This is a problem for the Young's double slit experiment. And it says, in a Young's double slit experiment, the angle that locates the second order bright fringe is 2.0 degrees. The slit separation is 3.8 times 10 to the negative 5 meters. What is the wavelength of the light? In order to do the problem, all we have to do is just choose one equation, and that one is that the wavelength equals the separation distance between the two slits times the sine of the angle at least I'm trying. There's my n, sine of the angle divided by the order of the fringe, and when we do that we would come up with a wavelength in meters respectively. Wavelengths are usually given in nanometers, and when I put the numbers on the graphing calculator, where'd it go? There it is. I would come up with, let's see, 3.8 10 to the negative 5 times sine of 2.0 degrees, two significant figures by the way, divide by the second order. That's an exact number here. So I come up with 6.63 times 10 to the negative 7. And when I convert that to nanometers, that would be in meters. When I convert that to nanometers, which is 10 to the 9th of 663 nanometers, or rounded 660 nanometers, and they don't say what kind of light it is. Perhaps it's the red line of the hydrogen spectrum, which would be at 656 nanometers. But in any case, the answer is 660 nanometers. The experiment is historically important because Thomas Young, who did it in around 1800, looked at light and figured that Newton's theory of light being particles, well, it seemed to work obviously for reflection, and he was able to have some success with it for refraction as well, but there were certain experiments where it just didn't hold up. So he showed that with this double slit experiment, the only way that you come up with the outcome, which is that you get these dark and light fringes here, so you get some kind of interference, is if in this experiment light is a wave. And so around 1800, about 100 years after Newton came up with the particle hypothesis for light, Young came up with the wave hypothesis for light, and it worked really well. It surpassed it, in fact. So light was established as being a wave. Then mid-19th century, around 1850, by Maxwell's electromagnetic equations, showed that it is in fact an electromagnetic wave. And then around 1900, when quantum mechanics came up, for example the photoelectric effect by Albert Einstein, it was shown that in some experiments actually light is a particle, and ever since we had what is called the particle-wave duality of light, and in some experiments light behaves as if it was a particle, sometimes it behaves as if it was a wave. As far as the double slit experiment goes, it is a wave, so I'm gonna have light shine from here on this one, and I'm gonna put a barrier, two-slit barrier in. I'm gonna put it about there, and I'm gonna make the slit separation larger because that's what it depends on. And then I make this one here smaller, about like this here. Then I show a screen, and then we get these constructive interference here and here and here and here. I could also show the intensity graph. Well, that doesn't add much to it. And destructive interference in between, and that is the outcome of the true of the experiment. Here's a photo of a laser shining through a double slit, and yeah, we get these constructive and destructive interferences, and the only way that could be explained is if in this particular experiment, and there are a few more, light is considered to be a wave. In fact, for refraction, actually, it's much easier to assume that it is a wave rather than a particle and come up with the correct results. This is the problem on a soap film, that is thin film interference. And I'll do the problem here in a little while, but first I want to explain it conceptually. So I searched for thin film interference on Google, and I came up with these kinds of images, and they almost all use light rays, which is fine because they're easier to draw, and very few of them use waves themselves, and that's the one that I want to show here. So here's the incident light as a wave, and it's being reflected, and our textbook describes that as it's reflected, it's inverted. That means if this is a crest here, then a trough is being reflected, but of course only partially it's being reflected. The other part is being refracted into the thin film, and then it's reflected down here, and again it becomes, if this is a trough here, then this one becomes a crest, and then it's refracted through here again, and then if these two are troughs, remember I described this one here as being a crest, so the opposite must be a trough, then if these two are troughs and then these two here are crests, then we get constructive interference, and that can only happen if the total thickness of the thin film, or the total travel path that the light ray makes through twice the thin film at whatever angle it does that, is an integer of one wavelength. So one wavelength, two wavelengths, three wavelengths, and so on. Then we would get trough on trough and crest on crest and have constructive interference. If the two are off by half a wavelength, then we would get trough on crest as they come out, crest on trough, and so on. So they're reflected, and through the thin film refracted light wave, that would then give us destructive interference. So if the condition is such that the light path here, the travel path through the thin film, is half a wavelength total, or 1.5 wavelengths, or 3.5, I'm sorry, 2.5 wavelengths, 3.5 wavelengths, and so on, then we get destructive interference. Now that could be also, notice that here we get a lot of these interferences, or these colors here at all kinds of different angles. So what happens here, for example, is that the light ray comes in at a certain angle and it produces its first order constructive interference, and then it comes in under a more shallow angle and it makes a second order here, and it comes out here, and we get constructive interference, and then even more shallow, and so on. So that's why we just not get one of them, but we get these thin film interferences in several places. And what we have here for constructive interference is one wavelength, this here for example, or we have two wavelengths if it's longer, or we have three wavelengths if it's even longer coming out of the thin film. And then of course the condition for destructive is add 1/2 to the number of wavelengths that they're apart, and we get destructive interference. I want to show this in a simulation applet. So let's see, I'm going to have one wavelength for the thickness here, and I think I'm going to start over again. Hold on. Okay, so one wavelength. Notice that here's the crest, and there's the trough, crest, trough, trough, crest, and so on. And then now here it's the same thing. This is a trough here, then that's too quick for me. If that's a trough, then this has become a crest, trough, crest, crest, trough, and so on. It comes out here, and what we get is constructive interference, trough on trough. That's at 1 wavelength. If I choose 1.5 wavelength, the same thing will happen, because here's the crest becomes a trough, here's the crest that becomes a trough, and the two come out here because the thickness now is 1/2 wavelength, but that means that the travel path is 1 total wavelength. Now if I change that one to 1/4 wavelength for the thickness, that means that the total travel path here would be 1/2 wavelength, and here comes the crest becomes a trough, the crest becomes a trough, but now because of the condition being 1/2 wavelength, here total down and up, when this one comes out and interferes with the reflected one, then we have trough on crest and trough, and we get destructive interference. And I think I forgot to mention it, but perhaps you have seen this here, that this is the incident light wave. This one is the reflected one on the top surface, and this one here is the formerly refracted one and then reflected at the bottom surface coming out. Another thing that you can see is that the wavelength changes. This here would become the wavelength in air, long wavelength, and then because of the index of refraction changing, that wavelength in the thin film changes dramatically. For example, for soap film, which is mostly water, it would reduce itself by a factor 1.33. We can see that even a little better if I change this here to 1 wavelength, and you can see, okay, here's a long wavelength, and now it becomes a quite short wavelength once it goes in there. Okay, I just wanted to show a few other things here. So these are the typical soap films and so on. The CD, if you look it up, actually has a very thin coating in the neighborhood of about 100 nanometers that allows thin film interference, and we see all these colors. Let's see, other kinds of examples, mostly soap bubbles, but even these guys here, I don't know what that is. I guess some kind of fly here. I didn't look up butterflies, but I did look up the peacock, who is here. Here's a butterfly. It says thin film interference. I looked this one up. This one goes back to thin film, except it's not a thin film as we think about it, like a liquid or so, but it's on atoms, kind of like a crystal, and what is called a Bragg reflection occurs there, which is itself based on thin film interference. So that's how we get these colors from a peacock's tail feathers. Alright, let's finally do this one here, and what we get is that I first should read the problem. So it says a mixture of red light lambda vacuum equals 661 nanometers and green light lambda vacuum equals 551 nanometers shines perpendicularly on a soap film and equals 1.33 that has air on either side. What is the minimum non-zero thickness of the film so that destructive interference causes it to look red in reflected light? So in other words, that means that the green light that it shines in would have to undergo destructive interference, and because the green light is at a different wavelength, that means that the red light is definitely not gonna what I should say, the green light is a different wavelength from the red light. That definitely means that the red light is not undergoing destructive interference, but to a certain extent constructive. Okay, the condition is, there's actually an example in the book that says as it has to travel through the thin film. Oh, it's not going to stay on this page here. It's going to be 2t is if it travels down perpendicular, and then for destructive interference it has to fulfill the condition of that when it comes back out it's half a wavelength off, and that has to equal then either, well, half a wavelength, but that's not going to get me anywhere because that simply means that t is going to be 0, or 1.5, whereas they write 3.5 wavelengths, or 5.5 wavelengths, and so on. Okay, and that's where they come up with the condition, well, the lowest one is going to be this one here, again, this one here would just yield that t equals 0, but that's what they said, a non-zero thickness. So in order to achieve this one here, with these, I subtract half a wavelength, so on the other side I have 2 over 2 wavelengths, which is simply 1, and that's how they then come up with 2 times the thickness, the travel path twice, perpendicular or normal to it, equals 1 wavelength, and therefore the thickness is going to be the wavelength divided by 2. Respectively, it's the vacuum wavelength divided by the index of refraction of the substance, because this one is actually the film, the wavelength which is within the thin film. So I'm going to plug in these numbers, and I'm going to come up with that the vacuum wavelength for the green light is where they want to have destructive interference, which is 551 nanometers. 551 divided by the index of refraction for water, which is what soap film is made out of, divided by 2, and that then gives a thickness of 207 nanometers for that one. Perpendicular out, it would be, the green would undergo destructive interference, and we would only see the red. This is the problem on telescope resolution, and it says 2 stars are 3.7 times 10 to 11 meters apart and are equally distanced from the Earth. The telescope has an objective lens with a diameter of 1.02 meters and just detects these stars as separate objects. Assume that light of wavelength 550 nanometers is being observed. Also assume that diffraction effects rather than atmospheric turbulence limit the resolving power of the telescope. Find the maximum distance that these stars could be from Earth. Well, here's what happens. Then look at these headlights here. If that car is close enough, then we can see the 2 headlights separately, and I guess we could try to gauge the distance to that one, kind of estimate it. And if it's further away, then these 2 kind of start merging together, and if it's yet further away, then we can really only see one, and it's hard to tell, hey, is it a car with headlights, or is it a truck with headlights where they're further apart but it's further away, or is it a motorcycle that just has one headlight? So what happens there is that our human eye, respectively binoculars and telescope, give us a certain limit of where we can see these 2 headlights or stars separately. Pretty much the geometry for this particular one goes as such that we're looking at different stars, and I chose here the Big Dipper for a reason. By the way, this is how you can find Polaris and North Star. Go off the last 2 and 5 times, and then you end up at Polaris and North Star, which is part of the Little Dipper. This star should be a little bit over here, and then this one should be a little bent down, but it's okay. Actually, the only reason why I took it is because of this star here, which looks like one star, but this one here is called Miser and Alcor. And here's a photo of these, and we can see all these stars here. And again, if you go 5 times this distance here, this way you end up at the North Star. And then you have all these others, and notice that there is indeed Miser and Alcor, a double star Alcor being quite a bit fainter, and if you have good eyesight, then you can actually resolve them into a pair. But there are plenty of double stars that are so close that human eye cannot resolve them, so we use a telescope, because a telescope's larger aperture has a higher chance of resolving stars. That's what the Rayleigh criterion describes. So according to that, we would have that the minimum angle that they could be apart from wherever we watch them equals 1.22 times the 1.22 comes from doing a more detailed analysis, times the wavelength divided by the aperture or diameter, the opening of the telescope or binoculars or the human eye, whichever one we're using. Okay, that's not all though. We have to look at the geometry, and I'm just going to turn this one here, and from Earth, let's say we're looking at these stars here, and they're very far away, and my Earth is going to be really tiny here, and I want to make it any smaller, otherwise we might lose it. And then I'm going to draw rays to here too, Miser and Alcor. So there's one ray. I don't know why this keeps jumping. Why does it keep jumping? I just want to get it right there. There we go. Oh, come on, stop doing this. And then I do the other one. And I have no idea why this keeps jumping. I just want to have, okay. Alright, so let me shift this one here. Okay, so here we're trying to look at these two here, and we have a certain angle in between here. That's the angle theta that we're going to come up with, angle theta. And we have a certain distance here, and we have a certain distance between these two stars, and I'm going to call it S, and that is given in the problem as well. And if we go back to the triangle condition, then we can relate that distance S here to the distance D to the tangent of the angle, respectively. When that angle is really small, then we can just say that S over D is that angle as long as that angle is in radians. So this small one here divided by that one is going to be, of course, a small number, and that describes this angle in between. So we're going to take this one here and then the equation from above. So SD equals this part here, and I'm going to move it over there. There we go. Use a little bit of eraser. This should be a nicer looking D. So I'm going to make it again into a nicer looking D, and that should have been a nicer looking equal sign. In any case, what we have to determine is this D here, which is D equals S, invert this one here, which means all of this is inverted and then multiplied by S, divided by 1.22, and I can get me some more space. That was supposed to be a 1.22, so I do it again, times the wavelength times D and that's going to come out to some unit that I'm going to figure here out on the calculator in a moment. Okay, S is given in the problem as that these two stars are apart from each other at distance of 3.7 times 10 to 11 meters. That's, let's see, is that 370 million kilometers, or 200 some million miles, which is kind of the distance between Mars and Sun. So assume that you have a binary star where two stars orbit each other as far apart as the Sun and Mars are, and that is possible, quite possible. So that's a number that makes sense. The other question would be, well, how do we know that? And there are other tricks we can use that would just extend this problem here too much. So 1.22 times the wavelength, and that's the 550 nanometers? Yeah, 550 nanometers. But I'm going to put that into meters, so 10 to the negative 9 gets it into meters, and that is divided by the aperture, the diameter of the telescope, so by 1.02, close that parentheses and hit enter, and I come up with a distance of 5.6 times 10 to the 17 meters, which is, I have to scratch my head, I believe it's 56 trillion. Actually, 56 quadrillion meters, which is 56. I take that back again. 560 quadrillion meters, which is 560 trillion kilometers, or in the neighborhood of, like, what is that, 400 trillion miles, or 100 light years, somewhere around there. In any case, so about 100 light years. In any case, that answer is going to be in meters if it's written as 10 to the 17. Oh, and then earlier I forgot to show a few pictures that I have on my own website, whose URL I never remember, so I have to Google myself. And I go to my own lecture notes and click on these one. I just don't know where it is. And here, for example, you can see the trapezoid in or trapezium in Orion, and you can see that in this low resolution image, they kind of start merging here. Well, in this high resolution image, they're quite nicely separated. We can see much more detail in this higher resolution image. Similar for Pluto and its moon Charon. Here they almost merge together. This, in fact, is the discovery image. And then the better the resolution of a telescope gets, the nicer they're separated. In this case, it means smaller is better, because this one is totally way too large. Pluto is apparently only very small here, and what good does it do if it's totally too enlarged, which is not the way it really looks like. And last but not least, very few binary stars or double stars we can actually resolve with a telescope. In this case here, they give us an example of something that's 100 light years away. Many other stars are further away, but we still know that they're binary stars, even though not even the best telescope can resolve them to be binary stars. So we're using other tricks, such as what's called a spectroscopic binary, where we have these two stars orbit each other, and as they orbit, they produce a Doppler effect in the spectrum, where the lines are shifting towards us, become blue shifted, or when it moves away from us in its orbit, they become redshifted, and we can observe that Doppler shift, and that tells us then that there must be a binary star, even though we cannot see it directly with a telescope. And actually, here it says the first spectroscopic system. It's just off the page here. Oops. That's okay. The first spectroscopic system was MISAR in 1889, not with Alcor, which is still not known if that one is actually in orbit around MISAR, but it itself is kind of like a double, triple, quadruple system, this MISAR here, and as it says, that was first discovered in 1889.